question from a very general book in the market available for the general relativity, which is the Wald. So this is a question number 3 from the chapter 3. So there are several other parts, but I found this particular part very interesting. That's why I have taken this particular part. So this is generally a discussion about the torsion tensor. So generally in the general relativity, the torsion tensor is 0, but in some situation it is not 0, like in the Einstein-Curtin equations you can see that it is not 0, but generally it is 0. Whatever you studied in the general relativity in the basics, it is 0. So actually here you can see that here this T and upper index AB is actually a torsion tensor. So here we have to prove that when we apply a torsion tensor to certain vector fields XA and YB, we get this particular result, as you can see here, and we're going to prove that. So let's see how we can do that. So first of all, before this, there are certain things you should know, that how we define actually the torsion tensor, which is suppose that you have this torsion tensor. So it is defined as the nabla A nabla V F minus nabla V nabla A F. So this is how we describe the torsion tensor in the general relativity, and since it is equals to 0 in the general case, we get that the nabla A nabla V F is equals to nabla V nabla A F. So this is what we get when we assume that torsion tensor is 0, and yes, it is 0. But actually, what is the geometric meaning of this particular torsion tensor? So we're gonna discuss this in a great detail in the next video, but here in this particular video only we are going to discuss about the tensor, only about this particular question. If you want a brief idea, you can think of this Riemannian tensor as this particular torsion tensor as the measurement of the, you can say that, the Christoffel symbol. What I mean is that this particular torsion tensor is also defined in a similar fashion, which is T, and it is equals to the Christoffel symbol, difference of the Christoffel symbol. But what's the thing is that there is the, suppose that we have Christoffel symbol ijk, so torsion tensor is ikj. So this is the meaning of torsion tensor, and if this is equals to 0, we get that the Christoffel symbol is symmetric. Yes, it is symmetric. So if you have seen anywhere that the switching of indices here in the Christoffel symbol is same, that comes from the fact that the torsion tensor in the general relativity is 0. We will discuss this in the next video also about the Riemannian tensor, because the torsion tensor and Riemannian tensor are constructed from the Christoffel symbol. Even this particular Christoffel symbol is not a tensor, even this, the fact it is not a tensor, still it is used to construct it. You will see that how the Riemannian tensor is whole, and you can see that its formula is completely based upon the Christoffel symbol. Okay, so this is a brief discussion about the torsion tensor, and this is how we represent it. Okay, this is very important. So now let's start the proof here. So for proof, I'm generally what gonna do is find out the commutator of the two vector fields. So what I'm gonna do is I'm gonna find the commutator of two vector fields, and using that result I will prove this. There are several different methods, but this is, like, you can say, not a very lengthy method, it's a short method. So what is the meaning of this is, I'm gonna do, suppose that we have x and y as a vector field labeled as a and b, and we are going to operate it on a function, and you will know that how to evaluate this, and I have also discussed about this in the Lie derivative video, that how it is related with the Lie derivative. Okay, so this is equals to the, okay, so it is equals this particular, we are gonna do a product rule, which is first of all x of a here and y of b on f, then that's Okay, here then a minus y of b x of a on this particular function f. This is how we define the commutator. You have also seen the commutator in the general relativity, in the quantum mechanics. In the quantum mechanics you have seen this, maybe in the form of the commutator of the position and the momentum, which is equals to, I guess, iota h bar. Okay, yeah, that is a representation. It is similar like that. So here we have a commutator and we define this using the product rule. Now what we're going to do, we are going to expand this, so it will take a little bit of space. So let's see what we can do here. First of all, writing it here as x of a and y of b. So, and this is equals to, when we try to expand this, first of all you have to know how we represent a vector field in the differential geometry. So here I am writing it that suppose that you have a vector field, let's say xa. So it is represented at xa and the nabla a. The nabla is the operator. And similarly for y of b, it is equals to y of, 1 minute, similarly for this y of b, it is equals to y of b and nabla b. Here generally it's the component of the vector field. Okay, this is nothing but generally the component of a vector field, and this is our basis vector. And generally the basis vectors in the differential geometry is the operator. This is the very general statement and you must have heard it. Okay, so now if I will try to write this in a more elaborate manner, what you will see is that it is equals to the x of a and nabla a and y of b. I am writing it bracket. I will try to explain this because this particular will operate on y b and then on particular function. Okay, y of b nabla b and here f. Similarly for here y of b and here in bracket x of a. Okay, so we have written this. Now I will try to expand it. First of all, this will act on, let me use another color, 1 minute. Okay, so first of all this will act on this, then this will act on this function. Okay, similarly this is the case for this particular part. Okay, now the commutator xa and yb, so this is equals to the x of a nabla a y of b nabla b f, and then minus x of then it will be like 1 minute, x of a nabla a, and this will, y will be in the first place because here we are not gonna try to do this. Okay, y of b, then here will be b then a, operate on this particular function f. So don't confuse, the expanded part of this is exactly this. Now we are going to write the expanded part of this here. It is a quite lengthy term, but we will figure it out. Okay, so this is the case here. Now minus, if we will try to do the same for this particular part, it will be y of b nabla b on x of a nabla a f, and similarly here if you try to expand this, plus minus will become minus and it will be y of b x of a and nabla a nabla b and f. Okay, so this is the expanded version, you can say. Now we'll just try to use some manipulations because it's easy to do the manipulation to get what we want. Okay, here what I'm thinking is we can, okay, here is a mistake. Here should be plus, here should be plus. I don't know why I've written here minus. Okay, now if we'll try to arrange it, let's see, it's x of a y of b and it is equals to, what I'm gonna do is that, see carefully, I'm gonna put this particular term and this particular term in a separate manner, and this particular term and this particular term here I will try to combine this. So what it will be like is that x of a nabla a y of b nabla b f. Okay, taking this term minus y of b nabla b x of a nabla a f, and here if I will take common y of b and x of a, you will be here left with this particular 1 minute nabla. You will left here with in bracket as nabla a, nabla b, f function minus nabla b, nabla is b, okay, nabla a f. So this is the expanded equation. I try to common the xa and yb, xa and yb from this particular term, and we get this. Now what I will do is that, see carefully, I will try to drop the function. First of all, see here, this is very important, that this is exactly our torsion tensor. Yes, see here how we have defined the torsion tensor here as the nabla a nabla b f minus nabla b nabla a f, and exactly this is what here written. Exactly this is what here written. So can I replace this particular thing with the torsion? Yes, absolutely we can. So let's do this. So we can here write it now as x of a y of b acting on function f is equals to x of a nabla a y of b nabla b f minus y of b nabla b x a 1 minute yb x a nabla a f minus y of b x of a, and torsion t here should be c a b, and here c, and here is our particular function. Okay, now what you can do here is that switching up the dummy indices, because yes, you can do this if you have studied tensor calculus. We can just change the dummy indices because it's our choice to label them, so we can absolutely try to do this. What I'm gonna do is that I'm gonna write the b to c, and in the place of c I'm gonna write b. So this is the place. So you will get at x of a y of c, and dropping the function f because this was our test function and its work is done, we can just remove it from our equation. You will get x of a 1 minute x of a, and this is the derivative operator on this particular y of c, okay, minus similarly y of c and del of c acting on x of a minus y of c and x of a 1 minute, here it is a mistake, we will mark, okay, y of b x b, c here it should be, I have changed y of c and x of a, this is our t b a c. So here we have changed indices. Now what I will try to do is I'm gonna choose this particular and shift it into this particular left hand side and this on the right hand side, and see what will happen. If this is the case, then it will be torsion tensor t b a c acting on y of c x of a, and it is exactly equals to the x of a, the nabla a on, and y 1 minute, here should be y on y of c here, and similarly minus y of c nabla c on x of a, and minus the commutator of this particular x of a and y of c. So this is our proof, because this is exactly what we have to prove, and this is exactly what we had to prove here, and we have done the proof here. As you can see that here we have to prove this tcab xa yb xa nabla a yc, and we have done this. There maybe you can see that here that in this particular expression why there is not c here, so I guess there is a mistake here while choosing the indices, or they are the dummy indices. Okay, so you can just try it on your own, and you can just replace it because these are the dummy indices. There is no mistake there. Okay, maybe someone has used here I j k, it's their choice, okay, because these are dummy indices. So finally we had done the proof. Actually this particular proof I have not done like in a very similar fashion, but you can say indirectly I have done this particular proof in the video of the Lie derivative, because when I try to prove that the commutator is exactly equals to the Lie derivative, this is the expression exactly what we got there. Okay, so I have proved it indirectly in the previous video, but not in the form of this particular torsion tensor. But yes, this is the proof. So thank you for watching my video, and this is particular Riemannian tensor. We will in next video will discuss our Riemannian tensor, what exactly it is, how it encaptures the parallel transport. You can use the Wald book, because there are not a very plenty of problems, but yet there are good problems. You can try like 10 to 12 problems. In chapter 3 I guess there are 10 problems, 8 to 10 problems are there. You can try that. And if you want some more questions in the general relativity, I have a plenty of resource. I will try to write all of the resources in the description box or in the comment box. Okay, so this is the video. Thank you.